we introduce ConeGS, error-guided densification using pixel cones for improved reconstruction with fewer primitives. 3D Gaussian splatting can produce highly detailed scene reconstructions, but this often comes at the cost of using many primitives. This limitation is mainly caused by inefficient cloning-based strategies that fail to effectively determine where to place and how to parameterize new Gaussians to maximize reconstruction quality. Let's start by seeing how densification is usually done in 3D Gaussian splatting and why it's challenging. In the original implementation, Gaussians that do not fit the scene properly tend to move significantly, triggering heuristic-based cloning or splitting. The resulting Gaussians inherit most of the parameters of the original and are then optimized independently. While various strategies exist to determine when cloning is triggered, including threshold-based, image space-informed, or random selection methods, most still rely on cloning. As a result, they inherit existing biases in color, shape, and placement, which leads to prolonged optimization and difficulty in thoroughly exploring the scene. Additionally, most methods do not directly use information about image space errors, which could indicate where placing new Gaussians would most improve reconstruction quality. This raises an important question. How can we use this information more effectively? Our goal is to directly introduce primitives in areas with high image space error, independently of the existing geometry, allowing them to be quickly adjusted to capture the missing details. To achieve this goal, we require a geometric proxy to determine the depth at which new Gaussians should be placed. To operate independently of the often unreliable existing geometry, we obtain this proxy from a quick iNGP reconstruction. Another important consideration is the initial size of the new Gaussians. We choose their scale so that after rendering they appear approximately 1 pixel wide. This enables them to quickly capture missing details without overlapping the existing reconstruction. The process begins with a quick iNGP reconstruction, which provides guidance for correct placement during both initialization and densification. Gaussians are initialized based on the depth from randomly selected pixels from the training data. Their parameters are then optimized in each iteration, while an error map is calculated. During each iteration, the pixels are additionally sampled according to this error map, and a point at the median depth from iNGP is selected. Each Gaussian is scaled to match the corresponding pixel cone size. These Gaussians are accumulated and periodically added into the scene to improve the reconstruction. To prevent inefficient placement of primitives, we directly penalize the opacity logits, applying steady pressure to retain only the most important Gaussians. We must also determine how many Gaussians to generate. This can be done either by using a predefined primitive budget, which offers explicit control over scene complexity, or by basing the number on the Gaussians already present in the scene, thus balancing the number of primitives removed with those added. Using our method, we achieve higher reconstruction quality compared to other approaches, particularly when working with a smaller budget, while also improving rendering speed for larger budgets. This improvement is consistent in both scenarios when the budget is explicitly specified and when it is determined based on fixed percentage of Gaussians added at each densification step. Visual comparisons additionally show how our better primitive allocation improves the reconstruction quality. ConeGS completely avoids cloning-based densification, instead offering exploration through iNGP, independence from existing geometry or inherited parameters, and achieving an improved primitive distribution within the scene. As a result, the reconstructed scenes require fewer Gaussians than other methods, while maintaining high reconstruction quality. Thank you for watching. To learn more about ConeGS, visit our project website or read the paper.